Whoa! This problem is from one of the hardest circuits exams I have ever encountered. This is a very tricky problem and an unintuitive problem designed to throw you off and make you panic during the exam. I want to show you how to solve this very hard problem, and in doing so, I hope you pick up my techniques and strategies that will be invaluable to you and help you perform well on the exam. So this is a Thevenin circuit with dependent sources, and there are 3 parts to this question, and we're going to get our hands dirty. Part A says, for the indicated load, use nodal analysis to determine Thevenin. Include a schematic of your circuit, worth 5 points. First things first, Thevenin is equal to V open circuit. So if we get this load and we cut it off and just have an open circuit, we can determine the voltage between those 2 points, those 2 nodes without our load, we'll have Thevenin. I'll show you the circuit. So here's our circuit. We removed our load, and now we just have to do plus minus V open circuit. So the voltage basically across this resistor, and that is equal to our Thevenin. The question asks us to do node analysis. So how about we just write the nodes? Let's choose this as ground. This is probably the obvious choice for ground. Ix is the dependent variable in question. Dependent circuits problems usually require you to find the dependent variable. So we're going to have to get Ix. We're going to have to get Ix. We're going to need VA because VA is Thevenin. I guess our third variable, we could use VE. Why VE? VE because Ix coming out of VE. That's a good idea. VC is connected to a independent voltage source, and that makes node analysis very tricky. We would have to do super node around here, and let's just not do that. Let's make it easy for ourselves. 3 unknowns and 3 equations. Now, dependent source problems, here's my first tip. Dependent source problems use analysis techniques to isolate the dependent variable. That's the whole idea. So we want to find a bunch of equations where we can get variables in terms of the dependent variable Ix. Ix, what is Ix? Is equal to VE minus VC over R5. There you go. If you do node analysis on VE, let's do node analysis on VE. Here's our equation from our node analysis. I wrote Ix because Ix is coming out. Instead of writing this, I just wrote Ix. Boom, 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 boom. We have VF. Here's the thing about VF. We can find VF in favorable terms. Remember what I said? Dependent source problems use circuit analysis techniques to isolate the dependent variable. So let's just do that. We know VF minus VA is equal to 2000 Ix. Therefore, VF is equal to 2000 Ix plus VA. Whoa. So we can just, put that in there, and, we get something like we eliminate VF, and now we get the dependent term in the same equation. And, we want that. That's the whole point. That's the whole point of dependent source circuits problems. So one thing we can note is that we know VE is equal to R5 times Ix plus VC. We could actually plug this into here. Now, we could do that. But I'm not going to do that. But you could do that. So this is equation 1. This is equation 2. Let's do analysis at node VA. And if we do that, well, here's our node equation. So that's that. VA, current going out, and I1 going in, which is actually 4Ix. And now this guy comes from the current going into VA. If we stated it that the current was going out to VA, the algebra would still end up like this. If we plug in what VF is, we have what we have is We have this guy, and this guy is our third equation. So now we want to find these guys, and if you put it in a matrix and you solve it, here's what you get. We know that Thevenin is equal to VA, and that is just 10.667 volts. And there's your answer for part A. 5 points. So part B asks, for the indicated load, use mesh analysis to determine I Norton. Include a schematic of your circuit. 5 points. So to find I Norton, if you remember the whole Thevenin concept, I Norton is I short circuit. So you just get the load and you short it, and then you can find I Norton. So let's do that. Boom, boom, boom. Here's the circuit. So here's the deal. I short circuit is I Norton. Now, well, it says do mesh analysis, so do mesh analysis. So we have I1 going, this way, I2 going this way, and I3 going this way. Let's do the I2 mesh first. We can write this from inspection. So here it is, and if you want to learn how to write from inspection, you can go watch my video on mesh analysis. We see this current source right here, and so to deal with this guy, the strategy is that we're going to do a super mesh. There we go, and now we can write the super mesh from inspection as well. Boom, boom, boom. So we have one equation right here, and we have two equations. So we have one equation and our two equation. And our variables of interest are, so here's the thing. One of the things that's interesting is that I3 is not in this equation, even though we're using the I3 mesh. Our unknowns are this. So, well, we generally want to find the dependent variable. That's how this works for dependent variable circuits. The way that we do this is this. So we see Ix, it's going this way, and it agrees with the direction of I2, but disagrees with I1, but it's being shared by both meshes. So here's what we write. There we go. And that's our third equation. We have three equations, three unknowns, and here's what we get. Boom, 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 boom. So we have these guys. But we also know that I Norton is equal to I3. Now, here's the deal. Remember the relationship between I1? It has a relationship for I1 and I3. So we may write this. 4Ix equal to I3 minus I1. The reason why we can do that is because I1 is equal to 4Ix, and it's the dependent source. So we also know that I3 is going here, and it agrees with I1, but it disagrees with, current source I1. Sorry, it agrees with current source I1, but disagrees with mesh current I1. So because of that, we can say that I3 is the plus and I1 is the minus. From this relationship, we can find I3 from I1 and Ix, and I3 is equal to minus 5.333 milliamps. And this is equal to I Norton. And there you go. That's it. So here's part C, and part C says, this is a very tricky part. This is the very trickiest of the trickiest. Here we go. Use the test voltage method to determine R Thevenin. You may use any analysis technique for the circuit. You can use the relationship between V Thevenin, I Norton, and R Thevenin to check your answer, but your R Thevenin result must be based on the test voltage circuit. Include a schematic of your circuit. All that's worth 5 points. Well, The test voltage is basically like, think about this. Because it is a dependent circuit with dependent sources, we cannot just use look-back method. Yeah, that will not work here. This is like kind of using the look-back method, but not really. What we have to do is we have to turn off independent sources. And we'll do that. But if the independent sources are off, the dependent sources are not powered. So there's a problem right there. And the way you solve this problem is by having a test voltage. That's how you do it. So here's our circuit that we're working with. For independent voltage sources, we short it, and that's how we do it. So it's off, but we have a voltage test in order to like turn on the dependent sources. Here's the deal. To find R Thevenin is equal to V test divided by I test. So we need to find I test, and we need to find V test. Well, here's V test. V test is 1 volt. Yep, it's arbitrary. We just select it. I'm picking 1 volt because, you know, that's easy. So now we just need to find I test. What do we do? How do we do it? What do we do? So here's what we do. Now we could use mesh analysis or we could use node analysis. What we did here is that we kind of just shorted this out. And so this whole thing is just ground. VC is just grounded. So like I think I want to do node analysis. So we just do VA. You know, this is still ground. This is VB. Remember, we want to isolate the dependent variable. If we do node, let's do node analysis on A. So for I test, we're going to say this. I test is going this way. The reason why we're doing that, because of passive sign convention. The current is coming out of the battery. So we're going to assume it's going in. So I'm going to put a plus. Plus I test. That's all equal to 0. So now VE minus VF, we want to deal with that. Say that I want to do this. Say I want to do node analysis at VE. This here is VE. Remember VE. We have the current going out, IX going out, this current going out. So I'll write it like this. So we have that. Actually, we know VF is still equal to 2000 IX plus VA. We can plug that in. So here is like an intermediate step. So this was VF, and I substituted that with that. So here's our equation. Here's another thing that I could do. Because VC is shorted, VE is just R5 times IX. So I could just do that. What we have here is we have 3 terms times IX. You know, this is IX, this VE, you know, this is R5 IX, R4 IX, and 2000 IX plus VA. So we just move VA to this side, and we just group all the IX terms together, and I solve for IX. And like, that's it, really. So if I go back to VA, we know what IX is we know VE is just R5 times X, and VF is just this guy right here. And we know IX, we just don't know VA. If I get this guy and plug them in there, if I plug them back into that equation, I will get something like this. Boom, boom, boom. Okay, so I have this, and what do I do with this? Here's what I do with this. We know that, we know from before that R Thevenin is V test divided by I test. And if that's just VA, VTest, R Thevenin, and that is just equal to 1 divided by minus 0.0005, 5? Yeah, 5. Minus 2,000 ohms. Guys, R Thevenin can be negative. Remember that R Thevenin can be negative. Here's the deal. I Norton is minus 5.333 milliamps. V Thevenin is equal to 10.667. 7 divided by 5.333 is 10 to the negative 3. This number looks like this number times 2. So this is just, oh wait, don't forget the minus sign. This is just minus 2,000. So it works. It's the same. We got it. We got it. Now, maybe you're wondering, like, what if I did mesh analysis? What happens if I did mesh analysis? Mesh analysis. So if I did mesh analysis for that circuit, we know that, VC is short. And so if I drew it like this would be a very, this would have lots of problems though. This would have lots of problems because we would have to have some kind of super mesh right here because of that current source. So if I redrew it to something like this, so we don't have to deal with that that guy. So 4ix would be over here, and we would have our 4 meshes. How you would deal with this is that to deal with this guy, we want to deal with we don't want 4 meshes. That's crazy. Let's just have 3 equations and 3 unknowns. One of them is going to be ix, because remember, for a dependent circuit, we're finding the dependent variable ix, or whatever it is, and we need to find that. So that's 1, and we're going to find a 5 matrix. No, we're not doing that. We're not gonna do that. 5 by 5 matrix. We're not doing that. No. Let's eliminate I4. We're not actually going to include I1. So to get rid of I4, we just do a source transformation, the whole source transformation thing. And we know VA, VTest, is equal to that, the new mesh, I3, times R1, times the dependent voltage source is now dependent voltage source. And this is our 1 equation. Now, our 2 equation comes from this I2 mesh, this I2 mesh. We just do it, from inspection, you can see. We have to see that we know what VF is, and we know I2, and we also know VE is, IX times 5. And that's how we're getting this, IX times R5. So we eliminated this guy by just substituting it with the dependent variable. This is another equation, actually. So here's our third equation. So with our 3 equations and our 3 unknowns, we have our deal. We have I2 is equal to this guy, I3 equal to this guy, and IX is actually 0. And if we do I-test is going out, so it agrees with I3 in the direction. So it's I3 minus I2, and it's the same. So if we did mesh analysis, we get the same thing. Now you can see why we don't want to do mesh analysis. We have to have this whole system of equations, this whole rearranging of the circuit, and that's just insane. That's just crazy. So we got to limit the scope of our variables. The node analysis was just so much easier. It was just so much easier. But here's the thing is that sometimes mesh analysis will be easier. So you just have to have a feel for it. You have to know what you're going to do. The thing is that solving hard exam questions require to mix and match circuit analysis techniques. Doing node analysis. Node analysis is really just KCL. It's another form of KCL. Now, one thing you also got to do is we have to use KCL and the passive sign convention to make sure our I-test is correct. Node analysis, when we did node analysis for this last part, we boiled it down to just 1 equation, 1 unknown. And that was just so much easier to compute than just doing a system of equations. To do the mesh analysis version, we would have to do all this craziness to the circuit. So here's the deal. One thing you have to do is that you have to think about your time and the points awarded for effort. The mesh analysis route needed a lot more effort for just 5 points. And the exam is designed to spike your anxiety. Ironically, if you mastered the material, your anxiety would be much less. But engineering students should know better. Sometimes you can't master the material in time. If a 5-point question is just too much, maybe consider the possibility that you forgot how to solve the problem. So skip it. The thing is that if you get 1 standard deviation above the average, that's a success. That's a successful exam. You did your job. So you don't have to get everything correct. Anyway, thank you for watching. Good night. Sleep tight. Don't let the bed bugs bite. Please comment. Good night.